Are you able to see the OneNote page?
Yes, sir.
Yes, sir.
All right. Now this is going to be a very interesting kind of thing. As somebody has said that he was not able to connect yesterday for the last few minutes, so I'm going to repeat some part. Now, when we talk about MOSFET as digital circuits, basically what are the digital circuits? They are simply the switches, or they are also used to be called as switching circuits. Okay, earlier. So digital electronics, as I was saying, is a subset of analog electronics, where I've already drawn the figure over here. It says that this particular margin that we allow is called as 1 or high, and this margin is called as 0 or low. So this is for our convenience that we are doing it. Okay, so you'll never see 1 or 0 explicitly in the laboratory. Okay, these are nothing but the voltage levels. Okay, this you must have already studied in your digital electronics.
Yes, sir.
Now, when we talk about the switching action, or the basic the switch that we are talking about is basic switch like this. Okay, I'll draw it again. Okay, so if I have circuit like this, a switch connected like this, and this is where I get the output. This is, let us say, the input voltage, or let us say the supply voltage in this case. Okay.
है क्या? अच्छा.
There is no current flowing over here. We call this R as a load in this case. Now, what is going to be the output voltage? Guys?
Yes, sir.
What is going to be the output voltage? It is going to be plus V.
Plus V ke barabar, sir, because it
Is it
is
correct?
acting.
And when I close the switch, what is going to be the output voltage?
Sir, 0, sir.
0 volts. Correct.
0, sir.
So we get two levels, first of all. Okay. Now, if I make the arrangement such that when I apply, let us say, some voltage over here, some positive voltage over here, then only this switch will be closed. Okay. So V in, I call this as. So if I have now the condition that is there is if V in is V or whatever voltage, then VO is 0. If V in is 0, then V out is plus V. Is this condition clear? I'm simply
Yes, sir.
making sure that. Just let me admit all. Okay, so if V in is voltage, positive voltage, then V out is 0. So don't you think this mimics what is called as the NOT gate? What is the truth table for NOT gate?
Sir, you please. Sir. हाँ.
Please mute your microphones. If V in is 0, V out is 1, 1, 0. So this is the truth table for NOT gate.
Yes, sir.
So what we are getting is exactly the same thing. This V, of course, this we are interpreting as 1. This low voltage is interpreted as 0. All right?
Yes, sir.
Now, in a similar way, I can have one more construct which behaves in a similar way. What is that construct? I have a switch here, I have a resistor here, and this is where I'm going to get the output. So this is V. Again, this switch is going to be controlled externally. Okay. Now when the switch is on, what is going to be the output voltage?
Sir, 0.
Yes, now I'm not going to allow anyone. Okay. If V out is, if the switch is open, or the switch is closed, what is going to be the output voltage?
0.
How can it be 0?
0.
The current is flowing
Sir,
like this,
it-
creating a drop here. In fact, this point is directly connected to plus V, no?
Sir, plus.
Yes? नहीं समझ में आ
Sir,
रहा है?
plus V. Sir,
Yes, sir. Yes, sir.
So what is going
sir,
to be
पहले
V?
आपने
सर पहले आपने सर्किट बोला था आगे.
हाँ सर,
Okay, I'm
पहले
saying
आपने
the
open
switch is closed. Very clear. Switch is closed. What is going to be the output voltage?
sir, it will be plus V then.
Plus V. If the switch is off, what will be the output voltage?
Then it will be 0, sir,
0.
because
Zero.
open.
Yes. In a similar way, I can make arrangement that this voltage is such that the switch is closed. Okay. When this is set, let us say a low voltage, and correspondingly, when I apply high voltage here, the switch will be open, and I'm going to get a similar kind of. So I have two different kinds of circuit doing the same thing. Okay, that is mimicking the behavior, or actually they are nothing but the digital inverting gates. Are you okay with this?
Yes, sir.
Now what I'm going to do is, let us say so in both the cases, the switches which are voltage controlled are off when VGS is equal to 0. Let us now replace this with the MOSFETs. So to implement or design a NOT gate, let us say with NMOS device, what will be the circuit? The circuit will be like this. So I'll simply replace the switch with an NMOS device, and this is where I'm going to have the input. This is going to be the output. Let us call this resistor R, load resistor. So this is V out, this is V in. Alright. Now,
So-
when will the device be in? When will the device be in triode region? Okay, let us first of all say that there is no voltage applied over here. In that case, MOSFET is in, the NMOS is in cutoff, isn't it? When there is no voltage here, when there is no gate voltage here at all, the MOSFET is cut off. Okay with that?
Yes,
Yes,
sir.
sir.
Right. Now, when I apply some voltage here, that is at V in, such that, so I'll apply V in equal to plus V itself. Okay. In that case, the MOSFET will first of all will go into triode region. Of course, I must make sure that VDS is small. So I will design this current such that VDS is very small. And when VDS is small, what is the situation? We have already seen the output characteristics. So this is your VDS, this is your ID, and you have such a kind of curve. Okay, this point we already know is VOV. And when we said VDS is less than VOV, my device is always in the triode region. So this region is what we are interested in. This part of the curve. Are you getting this? In fact, we must never allow the device, if I want to use it as a switch, I must never allow to go it into this region. Okay? So under the condition that VDS is less than VOV, if I apply V in, then my device will be on, it will be in the triode region, and now the picture changes. If you remember, the equivalent circuit for a Mosfet model, which is in the let us say we talked about the Mosfet switch. Okay, in one of the last lectures we have seen that the Mosfet model for in the as a switch was something like this. Do you remember this? This is drain, this is gate, this is source, and this is RDS. Remember this?
Yes, sir.
So naturally now this RDS will be coming into picture, and my circuit now takes this form. So if I replace it with the equivalent circuit, I get this form. This is going to be your V out. This is going to be plus V. This is going to be R. And what is going to be this value now? I am replacing the device with its model, switch model. So this is going to be
RDS.
Correct?
Yes, sir.
Is that fine with you?
Yes, sir.
So now, if you find out output voltage, this becomes a simple potential divider. So what is going to be the output voltage? Plus V into, yes?
RDS. RDS.
RDS divided by RDS plus R.
RDS.
Okay?
Yes, sir.
Now, ideally speaking, the device should have been what? When Vin is high, or when gate voltage Vg is made high, the device turns on, and when the device turns on, what will be the picture now? RDS will come over here. But ideally speaking, when the switch was on, if you look at the NMOS picture, at this picture here, when the switch was on, what was the expected output voltage ideally?
Was expected to be zero.
Zero.
The output.
But now there is a slight problem here.
Yes, sir. Because
Why? We already know that RDS is very small quantity. If you remember, RDS is a small quantity. Okay.
Yes, sir.
So this small quantity may be in some ohms, tens of ohms, divided by this tens of ohms plus some R, which may be in kilo ohms, let us say. Okay. So output voltage will not be exactly 0 volts. Can you calculate this? If this plus V is 5, so 5 volts multiplied by 10 ohms divided by 10 ohms plus 1K. How much is this? Come on, calculate this fast.
So 0.0495.
Please calculate this value. Please calculate this value.
So 0.0495 volts.
Okay, what is it? 0.0449,
495.
whatever
495.
volts. That is how much? 49 millivolts, nearly. But ideally, it was expected to be. Ideally, it was expected to be 0. So this is not an ideal switch, or this is not an ideal gate. This is not an ideal gate. So if I try to make a gate like this, it is never going to give me 0 volts when expected output was 0 volts. Okay, but it is very near to 0, so it may be called as 0, because as we have already said in digital electronics, there is a band of voltage, this one, which we have talked about.
Yes,
So I can call it as 0, no problem with that, but this will be called as a weak 0. Okay, it is not a proper 0, it's a weak 0, or also called as weak low. Okay, now let us evaluate the same thing for B in as 0. That is, the device is in cutoff. When the device is in cutoff, what is the value of ID? It's going to be 0, nearly 0, and it's going to be 0, isn't it? And what is going to be the output voltage?
Yes. Output voltage should be
it will be exactly plus V.
yes, plus V.
So there is no problem with the high value. You get a very good high value, exactly as the VDD. So this particular gate using NMOS suffers from weak low. This is one problem. Okay. Also, we have to make sure that R is such that the load resistance is such that whatever is the drain current, it does not make VDS large. Okay, so the design will be based on that. Okay, is this
Yes,
fine?
sir.
Now let us investigate what happens if I use the other topology. So the other topology will naturally employ a PMOS device. Please be careful with the symbol. So this will be plus V, this will be your input voltage, and this is going to be the output voltage V. Now, what is the condition for the PMOS? What is the condition for the PMOS to be off? Please remember, now the source is connected to plus V. So this will be the VGS. All right.
Yes, sir.
So what is going to be the picture now? When VG or V in is nothing but your VG, is equal to 0, then the device is on.
On, yes, sir.
All right.
Yes,
So
sir.
now if you replace this with the equivalent, this is going to be R. What is the value of this now? This will be RDS.
RDS, yes, sir.
Okay. Now what is going to be the output value? When the device is on, when your VG is 0, that is V in is 0, what is going to be the output value? Again, it's
Plus
a
V
potential,
into
so it is plus
The
V into
voltage
R divided by RDS plus R.
plus R.
Ideally, what this value should be?
Sir, plus VK equal
Ideally, V out should be equal to plus V.
plus V.
But because of this RDS, it is going to be slightly less than plus V. Let us try to find that out. Again, calculate this.
It's coming
Let us say
4.95 volts.
divided by 10 ohms plus 10, 1K. So what this turns out to be?
The 4.95 volts.
4.95. So you'll see that it is not an ideal value. Of course, 1K I am taking very, let us say, just casually. If you replace this, if this value itself 1K is less than, I mean, this resistor is less than 1K, if it is 100 ohms, then the picture is still bad. Do that.
Yes, sir.
Divide by 10 plus 100. So what will be
But in
the,
that case, it's coming as
what is the value now?
4.54.
Yes?
The 4.55 in that case.
Yeah, 4.5.
5. Sir, you are not audible.
Of I must make V in equal to whatever voltage, input voltage, okay, plus V. So if V in is, let us say, plus V, in that case the MOSFET, the P MOSFET is off, and then what is the output voltage there? When this
Sir,
MOSFET
it
Zero.
is
should
off,
be ideal.
it will be 0.
Yes, sir.
There is no problem. So I am getting a very good 0, but I am not getting a good high. So we can summarize that the gate or the NOT gate using only NMOS gives me weak low, and only PMOS gives me weak.
V high.
So these are not very good circuits for usage in digital electronics. Again, one interesting thing that is to be noted is about the power dissipation. Now, whenever the device is, let us say, when we talk about the switch, okay, I'll just make it very simple here. When the switch is off, what is going to be the power dissipation across the switch? What is going to be the power dissipation? How do you calculate the power dissipation? If I call this VSW and current flowing through that, so it will be the power dissipation across the switch will be I into VSW.
VS.
So what is going to be the power dissipation? What is going to be VSW?
E minus
This
V out.
plus
is
V.
But yes, it is going to be plus V, correct?
V.
Yes, sir.
Yes, sir.
Now, what is going to be I?
0.
0.
Excellent. So this is going to be plus V multiplied by 0. So what is the power dissipation?
Sir, 0.
0.
0 watts. Very good.
0 watts, yes.
So that is very good thing, no? There is no power dissipation at all. When the switch is
sir.
on, what is going to be the PSW? So this is when the switch is off and when switch is on. What is going to be the current will be very large, fine. But what is going to be the voltage across the device, across the switch?
0.
Yes, 0. So what is going to be the power dissipation?
Sir, again it will be 0 watts.
So an ideal switch, if I have an ideal switch, the power dissipation is very, very less. In fact, it is 0. Okay. But now in the case of NMOS, that RDS comes into picture when the device is on, isn't it? If you look here, the RDS comes into picture. This is the current flowing through the device. Okay. So what will be the power dissipation now? When the NMOS is on, what is going to be the power dissipation across the device? That is P NMOS, I'll say. It will be the drain current multiplied by, yes, in fact square into RDS on. Power is I square into R. Don't forget this one.
Yes, sir.
Okay, na?
Yes, sir.
Similarly, so when P NMOS power when off is going to be 0. No problem with here because ID itself was 0. No. Okay, na?
Yes, sir.
Now what about PMOS? When PMOS is on, again PMOS is going to be ID square into RDS, same thing. And again PMOS off is going to be 0. So you'll see here that both these technologies, both these methods do have a significant power dissipation. And why there should be no higher power dissipation? Can anyone tell me? Power dissipation should be one of the objectives is to reduce the power dissipation.
Because heat will be produced.
Yes, number one, heat is produced. Number two, this power is actually wasted in the form of heat. So if you are planning for a battery driven or portable device, your battery life will be lowered significantly if the power dissipation is more. Okay? And this is what all the TTL devices suffer from. I hope all of you know what is TTL.
Yes.
They use the bipolar junction technology and they suffer from heavy power dissipation.
High power dissipation, yes.
Okay. So first of all, my power dissipation is less but not completely 0. Alright? This is one problem. So there are two problems, that we have weak low, at the same time we have power dissipation, we have weak high, at the same time power dissipation if I use any one of these devices to construct the gates. So people found out that there is a combination. So we can combine NMOS and PMOS to give me a very good technology called as CMOS.
CMOS.
C stands for complementary.
Yes, sir.
Why they are called as complementary? Because we use both NMOS as well as PMOS in constructing the circuit. So how does the circuit look like? So it is very simple. You have, instead of that R, I am replacing it with a PMOS device. there is no resistor, and I am connecting both the gates together, and here is where I am going to get the output. So if I replace it in terms of switch models, it will look like this. These are all switches are controlled by the input voltage. So we make sure that when this PMOS and this NMOS they are never turned on at the same time. Of course, that is ensured by connecting the gates together and then applying the voltage over here, whatever is your input voltage. Are you getting this, guys?
So, yes,
So
sir.
we
So
come
can you
to
repeat?
what thing? What do you want me to repeat?
Sir, it cannot be closed at the same time. PMOS
Yeah,
and NMOS.
imagine this is the scenario. This is one switch, this is another switch. If you close both the switch, what will happen?
Sir,
There will be a short circuit, isn't
yes,
it? There will be a
yes, sir.
direct from V to connection from V to ground. There will be a short circuit. So we have to make sure that they operate in a complementary fashion. So at any
Okay,
one
sir.
given time, one of the device is on, the other is off. Got it?
Yes, sir.
Yes, sir. Sir, you are not audible.
Guys, am I audible now?
Yes, sir. Now you are.
There was a call drop. Okay. So we can say that, let us summarize the behavior of this device, of this circuit. When NMOS is on, with Vg greater than Vt, the P channel, the PMOS, is off, provided Vg minus V is greater than Vt. Now, when we talk about this CMOS, we no longer use Vt, but we use it separately for VTN for NMOS and VTP for PMOS. Please remember this. This is VTN and this is VTP. Similarly, when PMOS is on, with Vg minus V less than VTP, the NMOS is off, provided Vg is less than VTN. This should be simple to understand. So we say that this is a complementary MOS. So this circuit which I have shown is a CMOS inverting gate. and you can very well see its operation. What is the main advantage? What is the main advantage here? Have we solved the problem of week 0 and week 1? Yes? Guys?
Yes, sir.
How?
So, can you repeat the question? So, what were you asking?
How have we solved? My question is, how have we solved the problem with week 1 or week high and week low in PMOS and NMOS respectively? Okay, this is the question. So how did we solve that? Very straightforward to see that. One of the devices is always off.
Yes, sir.
So there is no question of any current getting, flowing, any current flowing directly to the ground.
Yes, sir.
And so there is no question of the potential divider like thing coming into picture.
Yes, sir.
All right.
Yeah.
So we have necessarily solved that by making sure that only one device is on at a given time. What about the second problem?
Okay, sir.
Power dissipation. Again, there will be no power dissipation because there is no current flowing. When this
Yes,
is
so current will be
when input is 0 and output is 1, one of the devices is going to be off. This device is going to be off. So there is no
Yes,
direct
sir.
flow of current from V2 plus V2 ground. Since there is no current, there is no question of power dissipation. All right.
Yes, sir.
So we have solved the problem of power dissipation also. So we can say that CMOS is characterized by very low power dissipation.
Dissipation.
In fact, there are two types of power dissipation parameters. One is called as a P static. Static means the levels are not changing. I have already applied 0 and I am having 1, and the device, the circuit is not changed. In that case, the power dissipation is going to be 0. The power dissipation happens to be in dynamic state. That is, when there is a transition from 0 to 1 and 1 to 0. So it goes from 0 to 1 and again from 1 to 0. In this part, there will be some power dissipation. So this will be the P dynamic. And other parts, it will be P static. For example, here, this section, there is no power dissipation. Okay, just one second. So in this section, there is no power dissipation. In this section, there is no power dissipation. Those green areas. Okay? Are you getting this?
Yes, sir.
Yes, sir.
So if I plot some kind of a power curve, you see that the power dissipation spikes like this, falls down again. So this power dissipation is going to be very, very small as compared to the other technologies. So we say that, in fact, this dynamic power dissipation formula is given as half C V square F, where V is the switching voltage, C is the capacitance of the oxide layer, and F is the frequency at which we switch on. This is for your extra information. there is a huge derivation behind it. I'm not going to go into that. Just remember that there is only dynamic power dissipation in CMOS devices. All right.
Okay, sir.
All right. So with that, we have seen the CMOS technology also, and there are a couple of things that are remaining to be tied up. There is one problem which I would like to discuss right now, and then we will say that officially this unit would be over. So any problems, any doubts with today's session till now?
No, sir.
And you
No,
will see
sir.
that the CMOS technology has revolutionized everything. So now all your smartphones, all your portable devices, smartwatches, tablets, they are all based on this CMOS
CMOS.
technology. Of
So,
course, there is a variation in that now also, but then basically it is CMOS technology only. If it would have been a bipolar technology, you would not have portable devices because they consume a lot of power.
yes, sir.
Okay. All right. Now see, I'm going to switch over to one type of problem that you may have. We are going to solve that problem in the class. So I hope there is no problem with this discussion regarding the MOSFET for digital circuits. Anyone has a problem?
No, sir.
Is there a question? Is there a question from someone? Guys, are you there?
Yes, sir.
Yes, sir.
Okay, I think the call
Yes,
again
sir.
got dropped. Okay,
Yes.
we will continue with a numerical example of this type. So
Okay, sir.
circuit that is given is something like this. Anyways, before going to the numerical example which I was talking about, we will see how to design the value of this R. So it is given as 5 volts. This R is what I am supposed to find out. So it is necessarily an NMOS inverter which I am trying to design. Okay. So given plus V is 5 volts. K is given as 0.5 milliampere per volt square. Vt is given as 1 volt. Your task is to determine R so that the low output level is 0.2 volts. This is what I was talking about. When the output is high, it is going to be the entire plus 5 volts, no problem with that. But what about the low? As we said, we are expecting a weak 0 here, but that has to be restricted to 0.2. Okay, so we are talking about the design. Let us see the solution. A low output implies a high input of 5 volts. So I'm applying 5 volts over here. So since the device, therefore the device should be in what region?
Triode region.
Correct.
Triode region.
So in triode region, what is the equation for drain current? You will recollect this. Do you remember this? Of course, we are neglecting the early effect and all this at this point of time. Simple model. Is this okay?
Yes, sir.
We've already seen this.
Yes, sir. Yes,
So
sir.
can I substitute the values and find out the drain current? This is going to be half
Yes, sir.
0.5 milliampere per volt square multiplied by 2 into VGS is what? 5 volts. We have said that input is equal to 5 volts VGS minus 1. What is the expected value of VDS? Here it is given low output level is 0.2. It means that
0.2.
yes, this is going to be VDS. So 0.2 minus 0.2 square. Yeah, solve this. Yes, come on. What do you get? Guys,
Sir, 0.39.
0.39. What?
Sir, amperes.
Amperes or milliamperes?
Sorry, milliampere, sir. Yeah.
Yes. So now can I find out R? It is simply B minus, that is VDD minus VDS by ID. What is VDD? 5 volts. What is VDS? What do I get? Yes? Come on, tell me.
Sir, 12.30
12.3 kilo ohms. Correct.
kilo.
Kilo.
All right. That's it. You have designed.
Yes.
You are not get. So this is the way in which the gate is designed specifically for the PMOS and the NMOS technologies. CMOS is out of scope at this point of time, so we can't say anything about that or do anything about it. All right.
Yes, sir.
Okay, so we are having very less time, but let me see if I can take up one type of biasing problem so that the completion of this unit itself. Meanwhile, you can just go through whatever we have seen.
Sir, can you explain once again about weak low and weak high? What is the concept?
Okay. Okay, then I think I'll concentrate more there rather than going for a new. Okay. Fine. So when I want for an ideal gate, for an ideal switch, okay, this is going to be controlled by your input voltage. This is V. So when the switch is off, what should be the output voltage?
Plus V.
Plus V. When the switch is on, what should be the output voltage?
0.
When we
0.
say we are, I said that digital logic levels are subsets. Digital logic levels are subsets of analog. So if you consider this from 0 volts to plus 5 volts, I'm going to call this range of voltage as high or logic 1. This range of voltage from 0 onwards to some value I'm going to call as low. Okay, okay up to this point?
Yes.
Anything between this is invalid. You all know that. In digital electronics, any value over here is invalid. All right.
Yes, sir.
Now, if I am having
So you're not audible.
is this a true low or a strong low or a strong zero? I'm just inventing this strong word now here. There is nothing called a strong zero or strong low, but I'm just for emphasizing. So this is near to the ideal. No, I mean it is ideal. This is value is ideal, whereas this is not ideal. 0.5 volts is not ideal. No, you should have had 0 there. But since you are having 0.5, I will call this very on the fringe of this boundary. I'll say that it is a weak value or a weak low. It means that it is a low value, but it is weak.
Weakly low. Okay, sir.
Okay. At the same time, if the value over at the output is suppose 4.5 volts, which is again on the boundary over here. So this value I will call as weak high.
Weak high. Okay, sir.
Is that fine? Have you
Yes,
understood
sir.
the concept? So in
Yes, sir.
Yes, sir.
reality, you will never get the ideal values of plus 5 volts and 0 volts for high and low, or 1 and 0. You will get about these values like 4.8 or maybe 4.7 depending on various different conditions. But as soon as it becomes 4.4, it tends to become invalid. Whereas 4.5, for example, I'll say it is a weak one. Getting it now?
Yes. Yes, sir.
Now these concepts will be very useful for you when you study digital logic design using a hardware description language, for example VHDL in the next or maybe next year itself. So please remember this very carefully. You see, those people who have missed the Mosfet session are going to miss a lot of things in life. पूरा का पूरा माइक्रो इलेक्ट्रॉनिक्स उनका बर्बाद हो जाएगा. They will not be able to understand anything. Anyways, so I think we have already crossed the time. So let me stop here for today. I hope there are no problems. There has to be some extra reading. Just do that specifically for CMOS and all those things, right?
Okay, sir.
Okay then.
Okay, sir.
Thank you.
Thank you,
Okay, sir. Thank you, sir.